Hey guys, welcome to another video. So today I'm going to do a video from the advanced syllabus on the topic of calculus, where we basically do curve sketching using differentiation. Now, this topic sort of starts off quite easy, but there are elements that are quite tricky, where we basically have a derivative graph and we have to sketch the original or vice versa. So the video series actually is a two-parter. The first part is going to do past paper questions where we basically look at stationary points, inflection points, etc. The next video, I'm going to do the relationship between the original graph, the derivative graph, and the second derivative graph. So two-part video series. So hopefully you'll like it now. And if you do, please like the video, subscribe to the channel, and tell your friends, guys. Now, before I dive in, I want to do a little bit of theory just to get us started, right? So curve sketching. So number one, curve sketching with differentiation. Let me just zoom in. Differentiation. Come over here. All right. Now, I want to cover two key points before we sort of dive into some of the past paper questions that I've prepared. Now, can you draw me this little roller coaster of a blue? Do you want blue? One sec. Yeah. Didn't want that. I want this. All right. If you're following, if you want to copy this down, feel free to. Right. So I want to draw a roller coaster of a diagram there. Now, I want to label three key things, right? First thing is, every time we have a turning point or a stationary point where it goes sad face, happy face, sad face, right? Those points there are called stationary points, right? Yeah, they have a zero gradient, so stationary points, right? For each one of these, perfect. And the thing about stationary points, so maybe actually, let me label these points. Let's call these A, B, and C, right? So A, B, and C are stationary points. Yeah. Happy for you to copy down these into your notes, right? Stationary points. Now, when do stationary points exist? It exists when the first derivative, the gradient, are zero. So for this one, when the first derivative is zero. Yep, cool. Now, a different color on here. Guys, when it changes, I call these mood swings, right? Because when the graph goes from sad face here to happy, right? In that point of change there, right? Let's call that point maybe D, right? And there's another mood swing over here where it goes from happy to sad, right? Somewhere in between there, here-ish, right? Point E. And another mood swing sort of from here to here, right? Up here somewhere. Call that point F. Now, three mood swings, they're all inflection points, right? IPs, right? An IP there, an IP there. So for D, E, and F, we'll say inflection points or IPs. And inflection points happen when the cavity function, right? The second derivative is zero. So when F double dash equals zero. Yeah. And then thirdly, right? A different color, maybe orange, yellow, maybe. Yep. We have a special point over here, right? That is both, right? The gradient at that point is flat, right? But also, can you see happy face there turning into sad? It's also a mood swing. So we call that, now let's call that point G. I call that a horizontal inflection point or a hip, right? So point G is a horizontal inflection point. Yeah. Horizontal inflection point. Now, there's no reason why I'm sort of squashing this up. So I'm just going to move this down a bit, right? Horizontal inflection point happens when both are true. First derivative is zero because it's flat gradient, right? And the second derivative is equal to zero because it changes concavity from happy to sad or sad to happy, right? Guys, those three elements need to be known when we're curve sketching today. That's the first point. Now, with the stationary points, right? Just want to highlight determining determining nature of stationary points, right? What that really means is sometimes when we find that a stationary point occurs at x equals to 3, we need to determine the nature, right? And what that really means is it a happy face or is it a sad face? Is it a minimum or a maximum, right? And there's two ways to do it, right? There's two ways to do it. So maybe I'll go method 1, right? Using second derivative, right? So very common, right? Where basically you go, if the second derivative is greater than 0. Now, greater than 0, if you draw a little graph, right? Greater than 0 means it's a happy face, but happy face means it's a minimum stationary point, right? Minimum turning point there, right? So therefore, yeah, maybe I'll come across a little too much. Yeah, therefore, minimum stationary point, right? If the second derivative is greater than 0. Similarly, or conversely, right? If the second derivative is less than 0, that's telling me that it's concave down or sad face, which has a maximum stationary point or maximum turning point at the top. Therefore, that's a maximum stationary point. Now, in the situation, right, where if the second derivative is equal to 0, so the first derivative is 0, that's how I knew a stationary point, and the second derivative is 0, this gives me a horizontal inflection point, right? Right? Which is basically like a cubic curve where I have a point there, it's flat and sort of changing concavity as well. Therefore, that's a hip, right? Horizontal inflection point. Guys, that's method number 1, right? Now, sometimes it's real. So this is using second derivative. Sometimes it's not pleasant or it just takes a while to find the second derivative. So we have the table method, right? So method 2, table method. And table method is very common, and it's actually the method we use to sort of verify inflection points as well. And what you do with the table method is you whip up a table. You have x over here, and let's say I'm testing on x equals to 3. Yeah, and then you sub it into the first derivative, yeah, f dash x there, right? Now, and the point here is that you test a little bit, so plus 0.1 and sort of minus 0.1 is a very safe thing to. Sometimes if 3 is the only stationary point, you can go plus minus 1, right? And it'd be it'll be safe as well. So plus minus 0.1 here, 3.1. Let's say this is 2.9. Now, when I sub all 3 of these numbers into this first derivative, I always get 0 here because that's how I got 3 in the first place. And let's say this is like 0.5 and this is negative 0.5. Right? What that's telling me in terms of the gradient, right? It's basically saying when I sub a number slightly to the left, it was positive gradient, right? The graph was going up. When I subbed it at 3, it was 0. When I subbed it slightly to the right, it was negative gradient. You can sort of see there, that's a maximum turning point, right? Maximum, therefore, maximum stationary point at x equal to 3. Yeah, that's the table method. So guys, putting this theory together, right? Yeah, we basically have a situation where I'm going to give you a few questions now, and we're going to use the theory for stationary points, inflection points, and hips, right? To try to sketch the graph. So they basically give you like a function, right? And you're going to apply this theory to it. And then generally speaking, they tend to ask you what the to determine the nature of the stationary points. Now, all up, all these questions are worth a lot of marks, right? So you've got to be able to do this type of question in an advanced paper. Advanced papers out of 100. These questions are like 6, 7, 8 marks, right? And there's a question later on from Karen, but I'll show you a harder version. It's worth, I forgot how much, but it's definitely like in the double digits, right? So if you can't do it, problem, right? All right, let's dive right in. So first question I have here, North City boys, classic, right? Classic question where they give you a cubic curve, right? In the graph, they give you a cubic curve, right? Sorry, that was a bit thin. Yeah, give you a cubic curve to basically sketch, and they ask you to find all stationary points, right? And determine their nature. There you go, right? All marks, right? Find the point of intersection. Now, sometimes when you find points of intersection, the question doesn't require you to test or verify, but when it's 2 marks, you're probably going to need to verify, right? And the last one, sketch, right? All right, this is, I couldn't get more classical than this question, right? In terms of curve sketching with derivatives, right? So let's go part 1. Yeah, let me zoom in. All right, let's do this. So, what I need to do, stationary points. So if I got y equals to x cubed minus 9x squared plus 24x, what I need to do is find the first derivative, right? 3x squared minus 18x plus 24. Yeah, to find stationary points, set that to 0. If I solve that quadratic, I'm going to get the 2 stationary points, and then I'll determine their nature. Yeah, quite straightforward. So let's go there. And what do I have? So maybe divide everything by 3. Yeah, minus, you know what? Before I do anything, I always say this in my class, right? Whenever I find the derivative, I always immediately then I highlight it, right? Because later on, I'm gonna need to, and then I'll put a box around it. I'm gonna need to use it to find inflection points, right? So just so I know which one was my original first derivative. All right, dividing by 3, you get that. That's nicely factorizable, right? Minus 2. X minus 4, and x equals 2 and 4. Great. So the steps are like this, guys. Differentiate, let it equal to 0, find the value of x, right? Solve, and then sub that into the original to find the y value so you can know where your stationary points are. So you go, therefore, right, stationary points at 2 something and 4, oops, sorry, 4 something, right? So to find these, I sub that into sub the x values into the original, right? So if you sub it into the x value there, so for example, this value here would be y equals to 2 cubed minus 9, 2 squared plus 24 times 2, right? And then you punch it in the calculator. Yeah. I think if you do punch it in the calculator, you get 20, I believe. Might want to check that. And if you punch the other one in, if you sub 4 in, I think you get 16. I want to check that as well. Yep. Now, I've got my stationary point. That's probably worth, what, 2 marks, maybe 3, to determine nature, right? So, determine, so test for max or min, right? Now, you can use second derivative. So for cubic curves, right, when you're sketching it, the second derivative test is probably the best one, right? It's the easiest, so I'm going to use that one. Feel free to use the table method you want to. So y double dash, right? So I'm going to differentiate this guy again. So it becomes like 6x minus 18, right? And then I'm going to sub the x value, sub my stationary points into here to see whether it's greater than 0. If it's greater than 0, happy face, minimum. If it's less than 0, sad face, maximum, right? So when x equals to 2, yeah, y double dash equals to 6 times 2 minus 18. Guys, what's that? 12, that's minus 6. Yeah, so when x equals to 2, it's minus 6, which means it's a sad face, right? Which means it's a, therefore, maximum stationary point at 220. Yeah. Oops. Yep. Easy. And now I sub in my other point as well. So when x equals a 4, 6 times 4 minus 18, that equals to what? 24. Positive 6. Guys, positive, right, is a happy face. That's a minimum. So therefore, minimum stationary point at, was it 416? All right, perfect. Yeah. All right. And that's 4 marks, right? Really chunky marks for that process, right? Done. And inflection points, really simple. So when I do inflection points, right, IPs occur when the second derivative equals 0, or y double dash, right? Same thing. So y double dash, I actually have it downstairs, right? What was it? 6x minus 8. So I'm just going to use that over here. So y double dash equals to 6x minus 8. So 18. I'm going to set that to 0. And then what's that? X equals to 3. Right? Now, normally, if it's worth 1 mark, you can conclude, therefore, inflection point is at boom. Right? But there are some cases where the inflection point doesn't work, right? So this one here, I got a test, right? So test for IP, right? And when you test for inflection point, you need the table method, right? So then you draw up X and second derivative, right? Because I want to see it change. I want to see the second derivative flip when I sub in a number. So that was 3. Now, technically, because it's 3, right? You don't have to go plus and minus 1. You can go plus and minus 0.1. You can go plus and minus 1, right? Doesn't matter, right? Because there's no other inflection points around you to change your picture, right? So you can go maybe 4 and 2. Now, subbing, where am I subbing these, by the way? I'm subbing these all into here, right? Yeah, I'm subbing them sort of into here and seeing what values I get. Definitely 3 is 0, because that's how I got it in the first place. If I sub 4 in, what's that? 24, that's positive 6. When I sub 2 in, negative 6. Guys, what that means is slightly to the left, I got sad face. Slightly to the right, I have happy face. In the middle, changing concavity, right? It flips. It's a mood swing. So therefore, I can now conclude inflection point at 3. Now, I haven't got the y value, so I need a sub y into here, right? So sub x into sub x equals 3 into the original, right? So if you do sub that in, I believe you get 18. Yeah, check that, please. But that's my answer. Pretty straightforward. Yeah, nothing hard about that, hopefully. Yep. Please copy that down if you're copying this down, right? And once we do that, guys, part 3, sketch. Now the sketch, you're just going to make sure you sketch your key features, right? So let me draw. Yep. I think that X is a bit bent, but yeah, doesn't matter. X, 0. No, since everything's sort of happening like in a positive space. Let's go over here. All right, so what do I know? 2 stationary points at 220, 416, not the scale, right? So maybe I'll move this down a bit. And that's the origin. So 220 and maybe I'll do 2 slightly over. 220 and then 416, not the scale. So what I have here, I got maximum turning point here, and I got minimum turning point there. Right, and I have to connect it easy, right? And now, what's the y-intercept, right? Have a quick look at the function. 0, right? Because when x equals 0, y equals 0. So I know I've got to pass through the origin. Okay. I'm going to get a curve that basically does that. So I'm going to rub these out. Oops. Rub these out. I'm just going to put dot there just so I can know there and there. Okay. So it's going to look like a little bit like that. And then over here, so it comes down and then it goes back up. Like that. Now, and then in the middle here, there's a mood swing, right? That is 3 and 18. Yeah, that's what you have to label. Yeah, label that point there, and that's your graph. Guys, how's that? So y equals to, what was it? X cubed minus 9 minus 9x squared plus 24x. And you're done. Hopefully that was okay, guys. So for this one, I mean, you can't get more textbook than a cubic curve with really nice roots, right? Looking like that. Yeah, can't be simpler. So I thought I'd start with that. Next question has a little, I want to show you a question with a hip. and then I'll show you a harder one with a lot of marks, right? So 3 questions from past papers. Guys, hopefully that was okay. Let's move on to the next question. So from same school, North Sydney Boys, 2007, so 10 years before that. All right, let's see what we got here. So consider the curve. Yeah, okay. This one's a quartic, para 4. Yeah. All right, what do I have? Turning points are the same as stationary points. Determine nature. And this time it's only worth 3 marks. Inflection point, or points of intersection. So there's 2 of them. Yeah, probably need a test. And then sketch. Do not find x-intercepts. Okay, cool. Easy. All right, let's do this. So part 1. Let me zoom in. So part 1, guys, if y equals that, then first derivative would be bring down the 4, 12x cubed minus 24x squared. Right, and the 6 goes away. Okay, that is, yeah, my first derivative. So I just want to highlight that. Cool. Set that to 0. When I set that to 0, maybe I'll factorize 12x squared out. Becomes x minus 2 equals 0. So I've got x equals 0 and 2 as my 2 stationary point x values, right? So I can conclude, I can go therefore stationary points at, also my little pre-conclusion, right? At 0 something and 2 something else. Yep. So I need a sub-0 into the original, so that would be 6. I can see it there. And if I sub 2 in to the x value, so I'm subbing 2 into there and there, right? 3 times 16, that hurts my brain. Someone do it, please. Minus 10, correct? Yep. Now, I need a test for max min, right? I need a determine nature. So once again, if it's a polynomial, I always use a second derivative, right? I always use a second derivative. So it's just quicker, right? So second derivative for this one would be what? 36x squared minus 48x. Yeah, so I'm going to highlight that as well because I need it for my inflection later. So when x equals to 0, y double dash, right, equals to 36, 0 squared minus 48, 0, which equals 0. Now, remember I said to you, if the second derivative is 0 and the first derivative is already 0, that's how I got it, right? Therefore, yeah, horizontal inflection point at, oops, yeah, at 0, 6. Yeah, so the moment you see second derivative is also 0, you can conclude it's a horizontal inflection point, right? So when x equals to 2, second derivative equals to 36 times 2 squared minus 48 times 2. Now punch in the calculator. What's that guy say? 6 times 4 minus 48 times 2, positive 48. Positive 48 means happy face. Happy face means therefore max stationary point at 2 negative, no, sorry, minimum, right? Because it's on the bottom. Yeah, minimum. Cool. So groovy. Is that okay? How many marks was that? 3 marks. Perfect. Now, got to do inflection points and then test for it, right? I might move these more vertically down so I get space to finish off the whole question on the same page. Therefore, hip there. This guy. Move him down here. Perfect. All right, let's do part 2 over here. Now, part 2 basically, to find the inflection points, second derivative, which is 36x squared. I'm reading that pink highlight there. 48x equals 0. Factorize 12x. It'd be like 3x minus 4. So x equals 0 and 4/3. Yeah, maybe check that. Now, I knew 0 was there because I knew it's a hip, right? I already know that it's a hip. So what I'm going to do, I need a test, right? Now, I already know that it's a hip, but let's test for second derivative, right? Or test for IP. Yeah. So for the first one, right, when it was 0, right, you can go, that's x, that's second derivative, put 0 there. Now, be careful here, right? So you can go whole numbers, you just can't go I'll just go like 0.1. Yeah, and I'll go negative 0.1. I know this is definitely going, so where am I subbing these, by the way? I'm subbing these into the second derivative, right? Which is over here, right? So sub it in, and now, so 36 times 0.1 squared minus 48 times 0.1. So this is negative 4.4. And when I go 36 times negative 0.1 squared, and that times that, that's 5.6. So that's telling me a change in cavity was happy face, then it became sad face in middle there. Perfect. So therefore, and I'll test the other one as well, right? I'll test 0, so that's 0, 0, right? Test the other one. Sorry, I definitely have to test it. I technically not sure where I needed to test 0, 0 because I already concluded that it was a hip, but just for completeness, I did. So now let's test 4 and 3. So with 4 and 3, you can instead of adding 0.1, maybe that's a fraction, that's 1 and a third, so maybe I'll test 1 and 2, right? Yeah. Basically, you need two numbers that straddle that without going over to the next value there, right? So when you sub 1 in, you get 36 minus 12. Sub 2 in, I think you get positive 48, and that's 0. So once again, you get sad face turning into happy face there. So you go, therefore, horizontal inflection point at 0, 6, right? And inflection point at 2 something. Yeah, I need to sub to 2 in. Oh no, not 2, and 4 and 3, right? 4 thirds. At 4 thirds something, right? If you sub 4 thirds in, so let me sub it in to the original. What's the original? Okay, 3 times 4 thirds minus, power of 4 actually. And just punching in the calculator. So minus 8 times 4 cubed. That plus 6. I got 94, negative 94 on 27, which is 3 and negative 3 and, okay, that fraction's a bit big. So need a bit more space. 13 on 27. Yep, that's my answer. Yeah, cool. And now I sketch, right? So when I'm sketching, 2, 3, let's come over here, give myself a bigish. Now can be negative, right? So yeah, good. Okay, what do I know? Stationary 0, 6, and 2, negative 10. So 0, 6, I got a horizontal inflection point at that point, and 2, negative 10, somewhere down here, right? So negative 10, right, and 2. So let me just, oop, oop, okay. Okay, perfect. That's 6, yep. That's why. Cool. So what do I know? Now, this is a positive quartic, right? Yeah, okay, cool. So I know there's a, so minimum, right? Has to be. Yep. I know there's a minimum stationary point down here, right? So it's definitely going to be happy face there. And there's a horizontal inflection point that looks like a cubic curve, right? So I'm going to cubic curve through here. I'm going to go all the way down. Yeah, all the way down, and then pop back up like that. And over here, maybe exaggerate it upwards like that. Perfect. How's that? Yeah, so sort of like a cubic curve down through 0, 6, all the way down for a minimum, pop back up, and that's my graph. Yeah, now, once you label that, where's my inflection point? 4/3. It's 4/3 and negative something, so 4/3, so this point here maybe. Call that point there. If you want to label that, that's like 4/3, or 1 and a maybe go 1 and a third, and that one there. -3 and 13 on 27. So that's when it goes from, you can see it there, right? Goes from sad to happy. Yeah. Guys, that's my graph. I'll do the final piece of labeling and I'm sweet, right? So I label 3x4 minus 8x cubed plus 6. How's that? So we sketched one that was very textbook before this. This one has a hip. That's how you do it. Let's do one more question. Now, the next question is from Karimba. Let's see how many marks there is. There's quite a lot of marks, I think. Let's count them. 3, 5, 10, 13 marks, right? 13 marks in a tuna paper. My God, if you couldn't do this question, it's not looking good, yeah? And how many parts? There's 7 parts. All right, let's do this. Let's work through this. So that's my function. All right, cool. Looks like something with a fraction there. So domain, natural domain, which is just domain, right? Show that, okay, differentiate it. Stationary point. So find the one stationary point. Nature, right? You're given the second derivative, okay? Prove inflection point, right? So I don't need to differentiate. Perfect. What happens to y as x goes to infinity? Draw, and then range. Okay, okay. Lots of marks, but nothing too hard about that. All right, let's go part 1. Actually, let's come down here. So, okay, part 1. Now, let me write the graph out again. So, x plus 1 over x minus 1 squared. Now, domain, right? Domain. That looks like oral x, right? Oral x, but x can't equal to +1, right? Because when x equals to +1, the bottom is 0, right? Can't divide by 0. So therefore, domain, oral 1, also oral 1, oral x can't equal to +1, right? Or if you want it in set notation, right? You write that as negative x, yeah, soft negative infinity to 1, soft, 1 to positive infinity, soft, and then union between the two. Yep. Is that okay? Done. So let me put this around that. All right. And box that. Guys, part 1's done. Part 2. And what's part 2? Just differentiate, right? Yep. Okay, cool. So now looks like when I differentiate this, I'm going to use the quotient rule, maybe. Call that U and call that V. Yeah. So it becomes like off to the side, U dash equals to 1 and V dash equals bring down the 2. That times by 1. Yep, that's my V dash. So my derivative, dy dx, they want me to. I could put y dash, but they wanted dy dx, so I'll do it. Quotient rule, right? So it's u dash v, so that times that, so x minus 1 squared minus v dash u, 2x minus 1 times x plus 1. Yeah, all over v squared. So v squared squared, so it'd be like 4. Let me just check that. Okay, I'm hoping one of these cancels out. So, oops. So let's see. Expand the top. I've got x squared minus 2x plus 1. So that's difference to 2 squared, so it'd be like 2 times x squared minus 1. X minus 1, 4. what I have here. Okay. I sort of get like on top m minus x squared minus 2x minus 1, is it? No, that's all right. And a plus 3 over. No, do I have any more space? No, I don't. Just a little bit more. Yeah. Okay, over x minus 1 4. Guys, this can be factorized, can't it? This guy here, that can be factorized. So let's go there. That becomes like negative squared plus 2x minus 3, which equals to minus plus 3 minus 1. So then great, that's exactly what I want, because then one of these cancels out with that to be a 3. And so the final answer now, I need a bit of space to write it. I'm just going to borrow just this. So therefore, dy dx equals to minus x minus 3 over x minus 1 cubed, which is exactly what they want. Yeah, not too bad. But you can see this one's much more intense already, right? The derivative compared to like a polynomial, this one's much more intense, right? Much more involved. All right, done part 2, part 3, find the stationary point. So set the first derivative to 0, find my stat point, right? So let's go up here. So I'll call it, I'll use their notation, right? dy dx, right, which currently equals to minus x minus 3 over x minus 1 cubed. Is that right? Let me check that. Yep. Set that equal to 0. When that equals 0, the bottom sort of disappears, right? Bottom disappears. So you sort of effectively cross that out, right? It's gone. And then x just equals to minus 3. Yeah? So, therefore, stationary point at minus 3, something, right? So, when you sub it in to the original, I think you get negative 1, 1, 8. Can you check that, please? So 3 on top will be 4 minus, yep, I think that works out. Now, determine nature, so test for max and min, right? Now, even though they gave me a second derivative in the next one, right? This one here, yeah, I don't want to differentiate that to get second derivative, but in the next question, they give you second derivative actually, but we're just going to use the table method, right? Because the point was, if it was too difficult to differentiate, I'll use table method, right? So this one here, so 7 minus 3 there. Now, there is no other stationary points, right? No, so I can actually use a nice jump and go minus 2 and minus 4, right? And sub that into the first derivative, dy dx. This is definitely 0. Guys, when you sub minus 2, where am I subbing it? I'm subbing it into here, right? Subbing into first derivative, right? Yeah, sub into the first derivative, and you get sub minus 2 in, and you get, into my calculator, and minus 2 would be negative 1 on 2 minus 2. Is this like, so you get like, let's just do it. It's a fraction. So minus 2, so minus 2, sorry. That's 2 minus 3 on top. And on the bottom, be minus 2 minus 1 cubed. 1 on 27. Put minus 4 in, minus 4, that's 1. I think it's the 1 divided by 4. Actually, the first one, when you put minus 2 in, I think that's minus, yeah, because it's like minus 2. Oh, but on the bottom is negative. Yeah, got it. So when you put minus 4 in, on the top you get positive 1. Let me just do it. So you get 4, you get 1 on top, yep. And the bottom, what's minus 4? My brain's not working very well tonight. Arrow 3. Minus negative 1, 2, 5. Good. Okay, cool. That's telling me gradient goes down, flat, back up, therefore. Yeah, therefore, minimum stationary point at, let me just check that, is it a minimum? Yeah, cool. -3, -198. Perfect. Guys, not sure how many marks we're through so far. Let's have 6 marks. Yeah, so 6 marks down. 6 marks down so far. Given the second derivative, proof inflection point for 2 marks. Okay, cool. Yeah, they've already done the hard part for me, right? Part 4. They gave me the second derivative. Now, what's the second derivative? That guy. Okay, cool. So second derivative equals to 2x plus 10 over x minus 1, 4, right? Because I'm finding inflection point, set this to 0. When you do, this guy's gone, and therefore x equals a -5, right? Which is what they want. Yeah. Now, but because it's 2 marks, right? I need a test. So test for IP. Where once again, table method. Yeah. Where x and the second derivative now, right? So you write second derivative like this. Yeah. -5 over here, so I can go -4 and -6. This is definitely 0. Now, where am I subbing this? Summing that into the second derivative, right? Yep. So when you sub in -4, you get 2 on top. Yeah. And then brackets -4 minus 1 to the power of 4, 625. Yeah, so that's positive. I'm hoping the other side's negative. So when I sub in -6, I get -2 on top. Yeah, definitely negative. So on the bottom, not that it matters, but -6 minus 1, power of 4, 2, 4, 0, 1. So what that's saying is it was a sad face and then becomes a happy face, right? In the middle. Mood swing, so therefore inflection point at -5. Oh, actually they only want at x equals to -5. They don't need you to get y value, but you know what? We're going to be a little bit sneaky, right? And sort of go, that point there is -5 something, right? Because I'll need it anyway. Yeah, so when you sub -5 in, I think you get -1/9. Yeah. All right, cool. Inflection point, I'm making good progress. Part 4 is done. Part 5, what happens to the y value as it goes to infinity? Okay. Let's have a look. So I'm just, this one here, I think I can squeeze it right down the bottom there. Okay, number 5. So for part 5, so the function is, what was the original? X plus 1 on x minus 1 squared, right? Now, which we know, if I expanded the bottom, right, using our limits, right? Because this is the limits, minus 2x plus 1. Yeah. So basically, it's asking me to find the limit as x goes to infinity of this y value, right? Of x plus 1, x squared minus 2x plus 1. Now, some schools don't teach this anymore, right? Because they don't consider it to be part of the syllabus. But basically, to find the limits like that, you divide by everything by the highest power of x, right? You get limit, and x goes to 0, also infinity rather. Divide everything, so you get 1 on x plus 1 on x squared. Divide everything by x squared, right? You get 1 minus 2 on x plus 1 on x squared. And the theory is, right, each one of these that has a fraction of x, when x goes to infinity, they all go to 0. All of them go to 0. So your answer is going to be 0 plus 0 on top and 1 plus 0 plus 0, which is going to be 0. Yep, and that's my limit. So you can say, oh, sorry. Do I have space? No, I don't. Oh, damn it. Yeah, I won't write this here. Just right here. I just need one more line to write a conclusion here. Okay, perfect. I'm going to write, therefore, when x goes to infinity, y goes to 0. My answer. Yeah. Okay. I'm getting all this information because it's all building up to part 6, which is a sketch, right? So let's have a go. So the sketch here, let's see if I can put everything together, right? Okay. Part 6. All right. Draw yourself an axis. Now, I think it's mainly positive. All right, it is good. It's good. Right. This is what makes this question quite good because the graph itself isn't that easy, right? I'll show you what a harder question looks like. Now, there's a domain that says all real x doesn't equal to 1, so there's an asymptote at 1, right? Yeah, so I'm just going to draw one. Yeah, looking like that, and then I'll select it, and then I'll dot it. So format, dashes. Oh, can't. Okay, so I'm going to have to do this. The insert a line. That's annoying. Yeah. Straight down, black, and then dash it. Yeah, maybe make it a bit thicker. Too thick. Okay. Okay. Not quite straight there, but that's fine. Guys, now what else do I know? That's the asymptote at +1. Okay. I know there's a asymptote. Where's my stat points? Stationary points. I know there's a stationary point at -3. So -3. So -3. And 1/8, right? So there, right? As a minimum stationary point there. Okay, interesting, interesting. What else do I know? Inflection point at -5. Okay, you know what? They're starting to tell me that this graph is very negative in the x, so I'm going to just move everything over. Yep. So -5. Now -1,9 is even smaller, right? It's like there, right? So okay, mood swing over there. So it should be like happy and then sad sort of thing, right? Okay, okay. What else do I know? That's it. Oh, and as x goes to infinity. Okay. So what that means is as x goes to infinity, this sort of goes to infinity as well. So sort of looking like this. As x goes to infinity. So I know maybe this side sort of looks like this. So that's asymptote and so it looks like, yeah, and x goes to 0, right? It goes, yeah, y goes to 0 when x goes to infinity. Okay, now this side, I know it's going to look like this, right? I know because this is a minimum stationary point, something it sort of bounces like this, and there's a inflection point here, so it goes from sort of happy to sad sort of thing, right? Action, yeah. And then now, what's the y-intercept? So when x equals 0, let me see. Let me just look. So when x equals 0, y equals 2 and 1 over 1. So 1, yeah. Okay, cool. So the y-intercept is at, at 1. Okay, great. Oops. At 1, somewhere up here. Yeah. So I think it's going to look like this, right? So it sort of looks like this. It sort of goes down, bounces up, and then sort of curves in. Now, the question here, right, is does it sort of curve and go up or not? So I think this is where if I sub in one big number, let's sub in negative, right, all the way -100, right? When x equals to -100, y equals to -100 plus 1, just a test, right? Over -100 minus 1 squared. Now that's definitely going to be -99 on something positive. So it's going to be a negative, what's that, -101 squared. So that's going to be a fraction, right? That's slightly negative. So I guess what I'm trying to say is it never comes up, right? It never comes up. It always stays very close, so almost like an asymptote. Okay, I think I got it. I think I got it, right? So I need inflection point over here. And you know what? I'm going to make this a little longer. Yeah, I'm going to make it a little longer just to get it there. All right. So it's going to do this. It's going to go like that. There, right? That's first part. And then second part is it's going to come, don't need this random dot here. It's going to go, yeah, there's my sad, and then becomes happy there. Like that. Nice. Yeah, and look like that, and then I'll label. So that point there as -1 on 9. And that's -1 on 8, and that's origin. Guys, let me just these dots. Yep, cool. How's that? Nice graph, right? Sort of looks like sort of broken into two parts, asymptote at 1, right? Curve that sort of looks like that. It's minimum, so it doesn't go anywhere below that, all right? And then it sort of comes up, but not quite breaches the x-axis, goes towards close to 0, but from the negative side. Yeah, and I got one more. Sorry, that was question 6, not question 4. My Roman numerals is broken, right? And then question 7. What's the range of this? Now, it looks like the range is from this point upwards, right? So then, quite simply, range. Now, if you wrote it like in inequality form, right, the range is going to be y is greater than or equal to -1 on 8, or y is an element, soft negative infinity, no, greater than, right? So no, hard -1 on 8, and then soft infinity. Actually, I'll put this whole thing. Yeah. Guys, that's my answer. Now, how was that? So this lesson was all about stationary points, inflection points, horizontal inflection points, or hips, right? Lots of marks involved in these questions. I mean, you saw it from like 7, 8 marks to, what's this, 13, did I say? 5, 13 marks, right? Lots of marks. Make sure you can do this topic. Now, next video, I'm going to basically do a video where I'm going to show you the relationship between an original function, its derivative, and second derivative graph. Guys, if you like that, please like the video, subscribe channel, and tell your friends. I'll see you at the next one. Thank you very much.